So my name is Yoshiharu Asaki. I'm from Joint ALMA Observatory. And today I will talk about not the scientific talk, but the introduce this technical commissioning story of ALMA high frequency long baseline capability for achieving the high angular resolution. And these are guys, members of the ALMA high frequency long baseline commissioning team. We started initialize the high angular resolution commissioning since 2017, and then this is so Anita introduced yesterday. This is a VOI Canis Majoris image with a 5 kilometer baseline in band 9, and this is a continuum image, and okay, and so now you can see a water maser image from blue shifted and systemic velocity around the systemic velocity and the red shifted component, and excuse me. And we still tackling the data reduction. So it's a very interesting image of the water maser distribution, because you can see in the blue shifted component, it seems that the blue shifted component cannot be observed at the position of the VY Canis Majoris itself, and it seems the blue shifted component is higher by the star or dust component, dust emission. And on the other hand, red shift component can be seen in the front of the star. So if we try to understand this image, there may be I'm not sure, but there may be an inflowing shell, maser shell, not the expanding shell. So it's very curious. So we still try to understand this image. But anyway, high angular resolution observation may dramatically change your science. So we have been trying to work very hard to unlock the high angular resolution image, high angular resolution capability using ALMA. So the answer is very simple: to use the longest baseline and to observe in highest frequency. But this is one of the most difficult things with ALMA. So anyway, we successfully achieved band 9 high angular resolution in 2017. And the last step of the validation of high angular resolution was conducted in 2021 to observe carbon-rich star R Lep within band 8, 9, 10 using the 16 kilometer baseline length. So in band 10, we could achieve 5 milliarcsecond angular resolution. This is the highest angular resolution using the ALMA. So why we selected the R Lep? Because VLTI measures the near-infrared photosphere with 15 milliarcsecond, and assuming the radio photosphere is factor 2 to 3 larger than the infrared photosphere, it can be measured and resolved using the ALMA 5 milliarcsecond angular resolution in band 10. So it is very good technical demonstration. And this source can be observed using the continuum emission. And 2019 has already detected the continuum source in band 10 using the ALMA. So this result encourages us to observe, to make a demonstration using this source. And in addition, this source has an HCN measures So very bright HCN measures. So it is very easy to detect this HCN measure. So we can also try to validate the image cube observation. So, and this is a result of the band 10 continuum emission as well as HCN measure emission. So the image is upside down, so the bottom is the north direction. And so you can see a hot color represents the dust emission, and cold color shows the HCN measure. And as already as the presenters showed, the HCN measure is surrounding the continuum emission like a ring-like structure. So it's very interesting result. So I think HCN measure will be discussed in the Katata later on Friday. So now I would like to focus on the continuum emission of band 8910. So so in 2021 high frequency high angular resolution technical demonstration, we observed not only in band 10 but also a band 8 and band 9 continuum source, and this is a continuum emission of band 8910 from left to right. But we have to know that the this is an image of the not direct source emission, but convolved emission, convolved image with synthesized beam. So in order to measure the source size, we make a model fitting for visibility amplitude. This plot shows the horizontal axis is UV distance or baseline projected baseline length normalized by the wavelengths, and the vertical axis show visibility amplitude from band 8, 9, 10 from left to right. So so we fitted the this visibility amplitude using the uniform disk fitting, and the result is shown like this. So as I said, the VLTI measures the photosphere, near infrared photosphere of 15 milliarc second in the diameter. So our result is very I think reasonable compared with the near infrared photosphere. But this result made us a little bit confused because okay, this image shows the Betelgeuse observation result conducted last year in band 6, 7, 8. And you can see that the photosphere, radio photosphere size decreases as frequency goes up. And this tendency can be often seen for oxygen-rich red supergiant and AGB stars. But this carbon star shows the opposite trend. That is, the disk size decreases as frequency goes up. So we need maybe update some model to describe to explain this radio photosphere change in as a function of the frequency. So this is a summary of my talk, and if you wrote an ALMA proposal in cycle 11, I think you already know that the ALMA will open the highest angular resolution image, highest angular capability from cycle 11. So we hope you will be able to get a very nice images with the highest angular resolution in cycle 11. That's all. Thank you very much.
I have a question about the errors in the size of the photosphere you saw in the previous slide. Whether, because the idea I got is that the radio photosphere you measure at different frequencies is consistent with the infrared photosphere, no? For R Lep. Is that?
Sorry.
That the size of the radio photosphere you show it for R Lep in like 14, 16, and 18 milliards seconds.
Yeah.
It's consistent with the infrared photosphere, but I was wondering about the errors in this radii.
Yeah. Yeah, right. And so actually, so the VLTI measures the photosphere near infrared photosphere with 15 milliardsecond. So
15, okay.
yeah. So those values seems to be smaller than our expectations before the observation. So that's another confusing matter for us.
What transition is it that gave you that HCN maser?
J1029, 890 gigahertz.
Which vibration state?
J1029. J equal 1029.
Yeah, is that in the ground vibration or an excited vibration state?
Sorry, I don't remember.
Okay. Right.
In the near infrared, we have smaller source sizes than in the radio, but that's the opposite of your trend.
Yeah.
Could you comment on why or where that might shift?
Sorry, at this moment, I cannot answer this question. So that's I would like to find an answer in the next paper about this result.